Okay. All right, so 5.2 is about exponential functions. And so this is going to be like a brand new type of function that we're learning about. We've learned about quadratic functions, rational functions, and radical functions. Okay. So now we're talking about exponential functions. So these are a little bit unique on their own. We are going to add these to our library of functions. They were not on the library of functions that I gave you in chapter 2, because the main way that you graph these is by using transformations. So we're going to learn about the basic shape of the base graph so we can add it to our library of functions. And there's actually 2 cases. So you can see 2 examples here, and this is actually breaking down the 2 cases for you. But I'm going to go over it. So the basic form of an exponential function is given by f of x equals a to the x power. So where x is a real number, a is greater than 0, so it won't be a negative base. And of course, a is not equal to 1, because 1 to the x power would just be x. And so this is called an exponential function base a. So pretty much what this is saying is, in order for it to be an exponential function, the variable needs to be in the exponent. Okay, so a couple of examples here would be 3 to the x minus 2 power. This is a exponential function because the variable is in the exponent. The base can be fractions, like 1/5 raised to the 2x power. This is also an exponential function. And then I think that's good for right now. So anything that has a, oh, actually, let me do one. I just couldn't remember. Anything that has a variable in the exponent. So another example, if I had -2 on the outside, but then I still had a positive base, and then I could even have -x plus 4 or something like this. This is also exponential function because, again, the variable is in the exponent. Okay, so you can see that in all of these examples here, I've added like extra stuff to it. Like, for example, in the first example, I had a -2 up there with my exponent. Then in the second example, I had a 2 being multiplied by that exponent x. And in the third example, I had a -2 being multiplied on the outside. I had a -x, or a negative being multiplied by the x, and I had a 4 being added to the x. So I'm highlighting all of the extra components that are not included in this form. And these extra components are going to be our transformations. It's what we're going to use to graph these types of functions using transformations. So we're going to learn the basic shape of the base graph, which would just be the base and the exponent x. And then we're going to use our transformation knowledge, which is going to be exactly the same that we learned in chapter 2. So all of the same rules to find the actual graph of functions like these. Okay. And then that little note down here says that we require the base a to be positive in order to avoid imaginary numbers that would occur by taking even roots of negative numbers. So our bases are just going to be positive with these. Now, I should have changed this. My bad. But I have a to the x written there in this form. But after this, I'm gonna really switch to using b for the base, but it's just the same thing. It means the same thing. I'm just, because this picture is the best picture I could find online. There used to be a better one, but I couldn't find it. And I like using b for the base anyways, because it's the base. It starts with the letter b. So you'll see me using b after this. And I should have really changed this to be there. I just was using the definition that they had on the PowerPoint. All right. So let's look at two examples here to learn about the basic shapes. So the first example is f of x is equal to 2 to the x power. So this is in that basic form, some positive number raised to the variable x. So in this case, our base, which is 2, is greater than 1. And when that is the case, when the base is greater than 1, then our function is going to look like this. It's going to be increasing from left to right. It's going to cross through the point 0, 1. Because if I plug 0 in for x, anything to the 0 power is 1, right? So as long as it's in this basic form, b to the x, my graph will always cross through the point 0, 1. And that's the point that they have given there. And then, of course, I could find a couple of other additional points just by plugging some values in for x. So if I plug 1 in for x, 2 to the 1 power is just 2. So that gives me the point 1, 2, which is right here. And the other one I want to talk about is if I plug in -1 to this function, f of -1 is equal to 2 to the -1 power. So this is where we need to remember our negative exponent rules. So if I have x to the negative n exponent, this is equal to 1 over x to the positive n. It's one of our exponent rules we learned. Remember, I would just make this a fraction and then I would flip it. So this is equal to 1 over 2 to the positive 1 power, which is just 1/2. So that's how they found 1/2 there. And that point would be right here, -1, 1/2. Okay, so that's just finding additional points other than 0, 1, because they'll all go through 0, 1, which we're going to see as I continue here. Another property of these base graphs, and I keep stressing that because I'm only talking about if it's in this form, if no transformations have occurred yet, is that we will have a horizontal asymptote at y equals 0. So it's saying the curve comes very close to the x-axis but does not cross it, not touch or cross it. So this is a horizontal asymptote that it actually will not cross. And again, this will always be true for exponential functions that are in this form, where no transformations have occurred yet. Okay? So whenever b is greater than 1, which is what's happening in this graph, we have what we call an exponential growth function. And that's why it's increasing constantly from left to right. And it's not just increasing, it's increasing very quickly. That's why it's like shooting up. So it's why it's called exponential growth. And the next one's going to be exponential decay. But these are important because they model like real life things in nature, especially. They also model things like not in nature, like accounting or finances, but like interest rates, the amount of that something grows in interest. But for nature, like these can model like the decay of a substance, like over time. So that's how we kind of use, that's kind of how we determine how old things are, by how long it took it to decay to the amount that it is now. I'm saying that right. And then like an example of exponential growth could be used to model like the population growth of a city, or like the population growth of, like, for example, a school of fish. You'll see that, well, if you go on to higher maths, you'll see that in examples. It's modeled for stuff like that. It's used to model things like that. Okay, so the other example here is f of x equal to the 1/2, equal to 1/2 to the x power. So in this case, my b is a number between 1 and 0. So it's not greater than 1. It's less than 1, but it's still greater than 0. So when this is the case, we would have a exponential decay. And that's why the image of this graph is decreasing from left to right. But the other properties are actually the same. It still goes through the point 0, 1. And it still has a horizontal asymptote at y equals 0. The only thing that really changed is that it's decreasing now from left to right. And of course, some of the other points will change as well. So now it's decreasing from negative infinity to infinity. Okay. Another thing I want to stress here is that f of x (1/2 to the x power). This is the same thing as 2 to the negative x power. Why is that the same? Well, this is the same thing as 1 to the x over 2 to the x, right? If I give both of those that exponent of x, 1 to the x is just 1. And this can be written as a negative exponent by bringing this to the top. So that's why this is equal to that. And so this is the graph of 2 to the x reflected over the y-axis. Because that's what we learned the transformation was when we multiplied the x directly by a negative. And I'm going to bring up that table Or I'm going to bring up a table that shows all of our transformations and go over them again. But I'm just saying that to you now. Okay? And of course I could find some other additional points here, which they have listed there, so I'm not going to do that. All right, so these are the two basic shapes of these graphs. So these are the two graphs that we would want to put into our library of functions. So again, if it's in this form, this is the base graph. F of x equals b to the x. So what I'm going to draw over here, which is really the same thing that's already drawn here, is what you can put on your flashcard for your library of functions. So the first one is if b is greater than 1. This is an exponential growth function. So it'll be increasing. It'll go through the point 0, 1. And it'll have a horizontal asymptote of y equals 0. And that's what you see here. Now, I don't know why they have this line here. It's the only thing I don't like about this picture. But this is the x-axis, the y equals 0, and then they have a vertical line through 1 for some reason. I don't know why they have that. But that is crossing through that point, 0, 1 right there, like I said. And then the other one is if b is between 1 and 0. Well, then it's exponential decay. So it's going this direction. But it's still going through the point 0, 1. And it still has a horizontal asymptote of y equals 0. So that's this graph. Okay, good. So, I have included a couple of other examples here of different types. Again, these are all in the base graph form. Some base raised to the exponent of x. So on the left, these are examples of exponential growth because all of the b's are greater than 1. And they can be decimals, that's fine. 2.5 is still greater than 1. 1.8 is still greater than 1. So all of these graphs here are going through the point 0, 1, and they all have a horizontal asymptote of y equals 0. But of course, some of the points are going to change because they have a different base, so that's why they're kind of spreading out on some of them. But those other two properties, well, three properties, the shape, whether it's increasing or decreasing, the 0, 1, and the horizontal asymptote. They will always be the same. And then the other one is exponential decay. Because all of those bases are numbers between 0 and 1. So 0.4, that's less than 1, but greater than 0. 0.25 and 0.7. All of those are between 0 and 1. So they're all decreasing, but they are also all going through the point 0, 1, and they all have a horizontal asymptote of y equals 0. All right. So we are now that we know about the general shape of these two types of exponential functions, we're going to use those two general shapes as our base graph, and we're going to use our rules of transformations to graph other types of exponential functions that have transformations in them. So and you can see a couple examples down here we're about to do. So I have the steps here. Of doing this. So step 1 is to determine if the base function f of x equals b to the x is an exponential growth or a decay function. So you're just going to be looking at the base and seeing if it's greater than 1 or between 0 and 1. And then step 2 is to find 2 additional points other than the point 0, 1, because we know that would be on our base graph. And we're going to sketch the general shape of that graph. And then we will use the transformations that are presented in the function to find our 3 new points on the final graph. And then, of course, we can always check our work with a graphing calculator. Okay. So let me leave those up there so I can explain what I mean. Okay. So step 1 also includes determining what the base graph is. So I'm looking just for the base and the exponent of x. That's it. So in this example, the base graph, number 1, step 1, would be, and I'm just going to write g of x, since that's called f of x, would be just 7 to the x. So I'm not including any transformations yet. I'm just determining what would my base graph be, and that's just the base and the exponent of the x. Okay, so here, b is greater than 1 because it's 7. So this is exponential growth, which means it's increasing. So I'm just going to sketch the base graph. I know that it goes through the point 0, 1, and I know that it's increasing. So step 2 is to find 2 additional points on this base graph, just 7 to the x. So I already know that 0, 1 is on there. Again, it'll always be on the base graph. So now I'm going to find g of 1. I'm going to plug 1 in just to find another point, and 1 is easy to work with. 7 to the 1 power is just 7. So this point 1, 7 is on this graph. Let's pretend like that's 7. And then if I plug in -1, this would be 7 to the -1 power, which is just 1 over 7. So that gave me the point 1, 1 over 7. And that point would be like right here, -1 and 1/7. So these are the 3 points that I found on my base graph. So this is just the graph of g of x. because you always want to start with the base graph, just like we did with the other transformations. We always started with like the regular x squared that went through 0, 0, and then used the transformation. All right, step 3. Is to use the transformations to find the 3 points on the final graph. So the graph of f of x, which is equal to 7 to the x power minus 2, is the graph of g of x, which is just 7 to the x, shifted down 2 units, right? Because I'm subtracting 2 from my base graph. And remember, when we would add or subtract a number to the entire base graph, that would shift it up or down. That's a vertical transformation. So that's shifting it down 2 units. So all of these points that I just found, I will just shift them down 2 units. So I'll subtract 2 from the y coordinates, because that's my up and down coordinates. So 0, 1, this point here, will become 0, negative 1. And 1, 7 would become what?
4, 5.
What'd you say?
I said 1, 5.
Oh, okay. I thought you said 4, 5. I was like, what? Yes, 1, 5. Perfect. And 1, 1/7, you just have to subtract 2 from 1/7, which you could do in your calculator, or you could do it by hand by getting a common denominator here. So this would be minus 14/7, which would be negative 13/7, which would be negative 1 6/7. But again, you could just type that in your calculator if you don't want to do all that mess. So that point would be 1, oh, this is supposed to say negative 1 up here, sorry. Negative 1, negative 1 1/7, which would be right about, or negative 1 6/7, sorry. To be about there. And so this will look like this. So let me recap. I went from 0, 1 to the original to 0, negative 1. And then I went from 1, 7 to 1, 5. And then I went from negative 1, 1/7 to negative 1, negative 1 6/7. So these are my new points. And these were the points from my base graph. Okay, and the horizontal asymptote on the base graph was y equals 0, because that's where it always starts. So where's my horizontal asymptote now?
-2.
-2, perfect, because I shifted it down 2 units. So that's the only thing that will change your horizontal asymptote is if you do a vertical transformation. That's the only type of transformation that will change that, if you move it up or down. All right. So I want to show y'all something real quick before we go to the next problem. If you go to Google, now it's working. Okay, cool. And you type in transformations of graphs. I don't know if it is the same for you, but for me, that first image there, it pops up. And I really like this card here. And again, like we've already learned all of these, but it's nice to have them all in one place here. And you can put all of this on your flashcard. And to be honest with you, you could actually print this out and bring it to the final if you want to, and have a flashcard. Okay? Everybody hear me say that correctly? You can print this out and still have a flashcard separately with your notes on the front and the back. Because this is a lot, and there will definitely be problems on your final exam that has to do with transformations, okay? So you can have this. All right, so we see that I'm just going to go over kind of how to read this card. Again, we've already learned these, but I'm going to go over it. So the first one says f of x plus d. So the f of x is our base function. So if I'm talking about what we're doing right now, that would just be the b to the x power. That would be my f of x, my base. And if I add something directly to that base graph on the outside, that'll shift it up d units. And the last column shows you how to get from one ordered pair of the original to the ordered pair of your transformed graph. So that's telling you to add d to the y coordinates, because that will move those coordinates up d units. Okay, then the second one is obviously subtracting from the function, so that moves it down. So we subtract d from y, the y coordinates. The next one is adding c directly to the x. So in what we're doing right now, that would be when we have something added in the exponent, x plus a number, so directly in our exponent. And remember, when we're adding or subtracting directly to the x, that's a horizontal transformation, and they're always kind of backwards intuitive. So if I add a number to the x, it'll actually move it to the left, which means I would have to subtract c from the x coordinate to get my new points. So that's what that says in the last column. And of course we have minus c, so I'll skip there. And then the two negatives are reflections, okay? So if I have a negative being multiplied by my entire base graph, so that means that in what we're doing right now, the negative would be in front of the b to the x, so in front of the entire thing, then that's changing my output values, which are my y values. So that would be a reflection over the x-axis, because if they were positive y, now they'd be negative y. And so we find those new coordinates by multiplying the y coordinates by a negative. And then if I have a negative being multiplied directly to the x, which is when it would be in the exponent of these exponential functions. So if you have a negative being multiplied in the exponent, then this would be a reflection over the y-axis, because now it's kind of changing my x values. So it's reflecting like that. And to find those new points, we would multiply our original x coordinates by a -1. And then finally, the last two, which are the most annoying, if I have a constant being multiplied by the entire base graph, then if that constant is, the absolute value is greater than 1, because remember, if this is negative, the negative will be taken care of in the reflection. I'm just talking about the number, not the negative part. That's the reflection. So that's why it says absolute value. So if it's not a fraction, then this will be a vertical stretch. And we will find those new coordinates by multiplying the y coordinates by that constant. And if it was a fraction or a number between 0 and 1, this would be a vertical shrink or compression. And same thing, we will find the new coordinates by multiplying the y coordinates by that fraction. And then of course, if it's being multiplied directly to the x, so in the exponent, then this is a horizontal stretch or compression. And we find the new coordinates by actually dividing the x coordinates by that constant. So this would be really useful for you to have for the final. Good? Any questions about that? Okay. So let's do this one. Okay. So for number 2, again, the first thing I'm going to do is figure out what my base graph is. Which would be g of x equals 4 would be my base. And again, I just want to have positive x up there. So this is what my base graph would be. My starting point, if you will. And this is just like when we did with the other graphs. If I gave you f of x equals, x minus 2 all squared minus 1, you would have to know that the base graph is x squared, right? Because that's the only thing that has an exponent of 2. So that's what I'm doing. I'm determining what my base graph is, which is 4 to the x. Okay. So b is greater than 1 again, so this is also exponential growth. So it'll be increasing. From left to right, it'll go through the point 0, 1, and it'll have a horizontal asymptote of y equals 0. So step 2 is to find 2 more points. So again, I already know that 0, 1 is on there. But I'm going to find g of 1, which is when I plug 1 into x. So that would just be 4 to the 1 power, which is 4. So that gave me the point 1, 4. So it would be around here. And then I can plug in g of -1 again, which would just be 4 to the -1 power, which would be 1/4. So this would be -1, 1/4, which would be over here. All right, and then step 3, we're going to start finding the new points using our transformation. So remember when we learned about transformations, I told you to always start with the transformations closest to the x and then work your way out. So in this case, I'm going to deal with the negative up here being multiplied directly to the x. So that's what I'm going to start with, which I'm going to say the graph of, I'll just use f of x, I guess. F of x equals 4 to the negative x. I'm not doing the plus 1 yet. Is the graph of g of x equals 4 to the x, sorry, reflected over the y-axis, because that's what that transformation does when it's negative in front of the x. It reflects it over the y. And so these points in blue of the original, to find the new points, I'm multiplying all the x coordinates by a negative 1. So this would still be 0, 1. 1, 4 would become negative 1, 4. And negative 1, 1/4 would become positive 1, 1/4. So just that graph would look like this. Everything flips over the y-axis. But my horizontal asymptote has not changed yet. Okay. And so now I have one more transformation to deal with, which is the plus 1. So all of these points will now shift up 1 unit. So the 0, 1 will become 0, 2. The negative 1, 4 will become 0, 4. Wait. I'm sorry. I mean, negative 1, 4 will become negative 1, 5. So I'm adding to the y coordinate. And 1, 1/4 will become 1, 1 1/4. So again, I'm just taking those purple points that I just found on the previous transformation to find my new points of my final graph for the 4 to the negative x plus 1. Because now I am adding 1 to the y coordinates. So 0, 2 would be right here. Negative 1, 5 would be here. And 1 1/4 would be about here. And my new horizontal asymptote would be y equals 1 because I shifted everything up 1 unit. Remember, that's the only thing that will change your horizontal asymptote. Okay. All right, let's take a break and then we'll come back and I'll finish part 2.